감사드리겠습니다.
Good morning, my name is Dat Nguyen, and today I will present about our study entitled as polycyclic aromatic hydrocarbon and their chlorinated derivatives in atmospheric particles from central of Hanoi, Vietnam. And our study will be focused on three main points: seasonal variation, sources, and regional transport. First, I will introduce about the two compound group, which is PAHs and chlorinated PAH. The PAH is the organic compound which mainly generated through the incomplete combustion of organic matter such as fossil fuel or biomass. The second, the chlorinated derivative, chlorinated PAH is the PAH derivative, which can be directly formed through the incomplete combustion of organic matter with the presence of chlorine-containing species, or secondary formation from the PAH with the reactive chlorine species. Next, I will say about why these compounds need the attentions. First, the PAH are classified by the IARC as the carcinogenic or possibly carcinogenic to the humans. For example, here the benzoyl A pyrenes is classified as the carcinogenic to humans. Meanwhile, the chlorinated PAHs are less studied than the PAH, but they show the higher AHR, which is aryl hydrocarbon receptor mediated effect, higher than some of their parents' PAH. So this means that even with the low concentration, chlorinated PAH can also affect and show the toxicity to human. Next, because these compounds are combustion related, so Hanoi is the relevant space to study them. In this figure, they show the four main emission sources in Hanoi. First, the traffic is very important because of the rapid urbanization and population growth will increase the private vehicle in Hanoi. Industrial and craft village will also show the emission through the combustion of coal, wood. Also, in addition, the combustion of rice straw burning and waste incineration are also the important local sources. So, together with these mixed sources, the Hanoi always show as the most polluted city in the world. Despite these emission sources, the previous particulate bound PAH study in Hanoi still left some research gaps. First, the short sampling periods will result in the seasonal variation are not clearly investigated. The source identifications was mainly based on the diagnostic ratio. So, although this method can show and identify the emission sources, but they cannot provide the geographical source area. And also, no previous study was investigate the atmospheric chlorinated in Hanoi. So, in this study, we measure the particle-bound PAH and chlorinated during the cold and warm periods, investigate their levels, profile, and seasonal variations, identify the emission sources, and evaluate the influence of the long-range atmospheric transport. So, to do this, we collect the atmospheric particle samples in central of Hanoi. First, the sampling site was located on the Hoàng Quân Việt Road. As you can see here, it is the major transportation corridor that connects the four ring roads. And also it was located in several, within the 20 kilometers of several industrial complexes. So this sampling site can represent both the emission from traffic and industrial. The TSP sample was collected using the high volume air sampler and quad filter filter. In the cold period, we got 12 samples from December 2019 to March 2020. And the warm period got 15 samples from May to August of 2021. So the collected filters were extracted and then analyzed for the target compound. The analytical procedure will include four main steps. First, the filter was added with surrogate standard and succinate extracted using hexane and acetone in 20 hours. Next, the extract was cleaned up using the silica gel multi-layer silica gel columns. After the concentration to 100 microliters, the internal standard was added and analyzed using the GCMS operated in the electron impact mode. So our target compound lists are shown here, and this is their abbreviations. So in total, we analyzed for 21 parent PAHs and 24 coronated PAHs. For the source identification, first we use the diagnostic ratios. This table shows all of the PAH's diagnostic ratio was used in this study. The diagnostic ratio can support the source identifications. So these ratio will compare the pair of the target compound, which vary depending on the emission sources. We also consider the diagnostic ratio for chlorinated PAH, but compared to PAHs, the diagnostic ratio for chlorinated PAH are based on only a small set of target compound. The concentration of the chlorinated PAH normalized by 1 chloropyrene and in this table, and 3 chlorofluoranthrene can identify some emission sources such as urban air, road tunnel, waste incinerator, and e-waste. So then to quantify the emission sources, we use the NMF, non-negative matrix factorizations. So in NMF, the concentration data matrix can be decomposed into source contribution matrix and the source profile matrix. So in this study, the NMF was selected instead of the commonly used EPA PMF because it was simpler to apply. They only require the concentration data matrix and without the uncertainty matrix. In this study, the concentration data was, only the compound with the detection frequency higher than 50% were retained in the analysis. So because of chlorinated PAHs had low detection frequency, so NMF was only applied to the PAH. So to obtain the optimal rank for the NMS analysis, we run NMS for rank from 2 to 6 with 50 run per rank, and then evaluate the cophanetic coefficients. The optimal rank was selected as the smallest value of K before the cophanetic coefficients decrease. So as you can see on this figure here, the cophanetic coefficient reached the maximum at 3 before sharply decreased at 4. Therefore, the final optimized rank was selected as 3 for the final NMF analysis. We also, one caution for when running the NMF is the source contribution matrix and source profile output is not unique scale. So the rescaling steps are required to derive the factor profile and contribution in the concentration units. Also, we calculated diagnostic ratio for each factor to support the source profile identification. So next, to identify the potential source area, we apply the PSCF. First, the 5-day or 120 hours backward trajectory were generated using the high split. In total, we obtained 288 trajectory in cold period and 360 trajectory in the warm period. Next, the PSCF method will combine the backward trajectory and the measure concentration of the pollutants using the JustStat plugin in the Meteor Info Map software. So in PSCF, the high PSCF results will indicate the potential source area where the air mass passes before reaching the sampling sites during the high concentration event. The high concentration event is defined as with the threshold, which is set as the 75 percentile of the total concentration of both PAH and chlorinated PAH in this study. And finally, the PSCF map was generated using the ArcGIS with the IDW is the inverse distance weighting interpolations. With this method, now I will move to the results. The mean concentration of PAH is 80.5 nanogram per cubic meter and 6.92 picogram per cubic meter for chlorinated PAH. The both compounds group will show the higher concentration during the cold period than the warm period. So this related to the lower temperature at the cold period will enhance the partitioning onto the particles onto the particle. And also during the warm period, as this sampling site was located in the educational hub, so the school vacation in Vietnam was in the summer, so it will also reduce the activity of the traffic near the sampling sites. So now let's compare the pH and chlorinated levels between Hanoi and Korea. First, let's take a look at the Unsan study, which report both gaseous and particle phases of pH and chlorinated. In this study, our pH level was 80.5 nanogram per cubic meter, so which is significantly higher than in Unsan, which only at 4.57 nanogram per cubic meters. Meanwhile, the concentration of chlorinated pH in our study is 6.92 picogram per cubic meters, which is lower than the chlorinated pH in the Unsan study. So this may be explained by the difference between the characteristics of industrial in the two cities. In Unsan, Unsan is one of the most largest industrial city in Korea, and it was famous for the petrochemical, shipbuilding, and chemical manufacturing industry. Meanwhile, the main industrial sector in Hanoi are less reliant on the fossil fuel combustion, so it will get the lower concentration of chlorinated pH. Now let's compare the levels between the capital of the two countries, Hanoi and Seoul. The concentration of particle pHs in Hanoi is 80.5 nanogram per cubic meter, while the gaseous phase shows 166 nanogram per cubic meters. Meanwhile, in Seoul, at the gaseous phase, the concentrations were only 30.9 nanogram per cubic meter. So the both studies shows that the concentration of pHs in Hanoi is higher than Seoul. Now I will move to which compound are dominant for these concentrations. So the profiles of the pHs were dominated by the low molecular weight compound, and the red boxes show the three most dominant is phenanthrene, phoranthine, and pyrenes. And these compounds are the indicator of mobile sources and straw burning. So the highlighted low molecular weight pH show the higher concentration during the cold period. This can be explained by the low temperature will increase the emission from the gaseous from the gasoline vehicle during the cold phase and the warm up phases. Also enhance the condensations onto the particles. Meanwhile, during the warm period, the school vacation also affect and reduce the effects of the traffic emissions. The high molecular weight pH were relatively higher than in the warm period. This can be related to the emission from the coal combustion and the straw burning. Although the straw burning and coal combustion can emit more low molecular weight compound than the high molecular weight compound, but the high molecular weight compound are mainly particle associated, so it can be transported into the sampling sites. So this profile will be more informative when comparing with the profile in Korea. So the particle phase profile of the pH in our study showed the dominance by the low molecular weight compound. But this is somewhat unusual because normally the particle phase profile is expected as show the high contribution of the higher molecular weight compound, which this expectation is also shown in the study in Unsan. So interestingly, our study showed the visually closer profile to the gaseous phase in Seoul. The gaseous phase result in Seoul, which is dominated by the low molecular weight compound. So this can be explained by the two main mechanisms. The first one is the H particle transported over the long distance can form the surface coating, so which can trap the low molecular weight compound inside and protect them from the gas particle exchange or the photodegradations. And the second one is And the second one is the local emissions, such as traffic and biomass, can also contribute to the large proportion of these compounds. Now let's move to the profile of the chlorinated pHs. The profile of chlorinated pHs is also dominated by the low molecular weight compound, which is the monochlorinated 3-ring compounds with dominance, especially the 2-chloroanthracene and 9-chlorofluoranthrenes. The low molecular weight compounds show the higher concentration during the cold period. Meanwhile, there was no clearly seasonality was observed for the high molecular weight compound. So let's compare the profile between the chlorinated pH compound profile between Hanoi and Ulsan. So in our study, the profile was dominated by the low molecular weight compound, especially the 3-ring compounds. But if we look only at the dark blue bar on the right side in Ulsan study, we can see that it was dominated by more heavy compound, which is like 4 and 5-ring pHs. So this can be explained by the stronger influence of the industrial activity in Ulsan. Meanwhile, the Hanoi was more influenced by the urban, such as traffic emissions. And now I will talk about the source identifications. If we look at the scatter plot here of the diagnostic ratio for the fluorine and over fluorine plus pyrene, all of the sample was fall into the gasoline emission range. This indicates the strong emission from the traffic. Meanwhile, the ICDP-based ratio will show more seasonal difference. Most of the warm period sample was contributed by the petroleum evaporations and the traffic emissions. Meanwhile, the biomass emission may be contributed by the straw burning emissions. In contrast, for the cold period, as you can see here, almost all sample fall into the grass, wood, and coal combustion emissions. This can be, let's take a look at the high BEP over the BAP ratio, which suggests the influence of the long-range transport emissions. So this would also be supported by the windrows during the cold period, which show the prevailing wind direction is the northeastern. As you can see from the fire map, the regional vegetation fire and also the coal combustion for domestic heating in China can be transported to the sampling site. Unfortunately, the diagnostic ratio for chlorinated pH were not included in the final interpretations because the low detection frequency of many chlorinated pH compound. So for more quantitative source identification, we apply the NMF. The NMF in this study show 3 factors, and now I will more detail talk about these. For the factor 1, the key marker compounds were phenanthrene, anthracene, and fluorine, which indicate the vehicle emissions, including gasoline and diesel, together with the fluoranthene and pyrene, which indicate the straw burning. The diagnostic ratio also support the emission from gasoline combustion, petroleum evaporation, and biomass burning. So therefore, the factor 1 was assigned as the traffic and straw burning emissions. Let's take a look at the panel B. The factor 1 show the most dominant sources of pH, which accounting for 87.8%. So the mean contribution in the cold period was higher than the warm period, and this factor was assigned as the traffic straw burning, and these differences were likely affected by the traffic emissions because although the straw burning is relatively higher in the warm period, but their short duration is likely limit their effect on the seasonal mean contributions. The factor 2 marker compound indicate the coal combustion and waste incinerations. The diagnostic ratio also support the grass, with coal combustion and pyrogenic sources. Therefore, the factor 2 was assigned as the coal combustion and waste incinerations. Let's take a look at the panel B. The factor 2 was the second most dominant sources of BAH, which only account for 8.5%. The contribution of the factor 2 in the coal period was slightly higher, and this can be explained by the contributing source between the two seasons. Although the coal-fired plant near Hanoi and waste incineration can affect Hanoi throughout the year, but during the coal period, maybe the coal combustion for the domestic heating in China will only affect Hanoi during the coal period. For the factor 3, it was assigned as the industrial emissions, and these factors will only contribute to 3.7%, and which is consistent with our interpretation before, is the main industrial sector in Hanoi are less reliant on the fossil fuel combustion. And finally, I will identify the potential source areas. First, I will talk about the BAH. So for the BAH during the cold period, the potential source area mainly come from the northeastern regions, especially Anhui province in China, and coastal area between the Fujian province and Taiwan. And the emission from these locations are likely coal combustion and biomass burning. During the warm period, the BAH might reach the sampling site from the western and southwestern regions. First is Andaman Sea and the Bay of Bengal near Myanmar. As you can see here, this region is mainly oceanic, but the BAH detected here is maybe not only the ship emission, it can be also the emission from the coastal city of Myanmar, and then transported to the ocean and transport back to the sampling sites. Next is northern, and the other source area can be northern Thailand and Yunnan province in China. Next, for the chlorinated source chlorinated BAH source area during the cold periods, the coastal area of Fujian province in China again was identified. This is very similar to BAHs, which suggests that the chlorinated BAH and BAH they can show the common sources. They can share the common sources. And interestingly, we can see another potential source area is in this ocean area, which can be explained by the photochemical formation of chlorinated as the process as shown on the slide. First, the BAH can be excited by the sunlight, which create the reactive species. Then these reactive species can react with the chloride ion to form the chloride radical, and which is subsequently react again with BAH to form the chlorinated BAH. And in these marine regions, the sea salt aerosol can provide the chlorine ions for these processes. And during the warm period, for chlorinated BAH, the potential source area is from the eastern and central of Thailand. And from this area, we suspect the emission from the industrial activities. So to conclude, the particle-bound BAH and chlorinated BAH were measured in Hanoi during the cold and warm periods. The level of the both compound group were higher in the cold period. The dominance of the low molecular weight compound likely reflect the contribution from both local and emission and long-range transport. The sort identifications identify the common sources for both BAH and chlorinated BAH, including fossil fuel combustion, straw burning, and waste incinerations. The potential source regions show the clear seasonal pattern with the eastern and northeastern influences in the cold period and western and southwestern influences in the warm period. This study will provide the first monitoring data on the atmospheric chlorinated in Hanoi and highlight the need to manage both local and transboundary air pollution. So before finishing, I would like to emphasize one message. Our study was conducted in Hanoi, but their main implication was not only limited in Vietnam. So our study results show that the toxic organic pollutants are influenced by both local emission and the regional transport. So Hanoi can be considered not only as the local pollution in Southeast Asia, but it also a part of the Asian transportation atmospheric system. So this result is important because it's also relevant to Korea when the need to consider the transpiratory air pollution while studying about the toxic organic pollutants. So this is the end of my presentation. Thank you for your attention.
Thank you. 혹시 질문 있으실까요?